Okay, then chapter 5, that is work, energy, and power of class 11 NCERT. Now let's see the introduction. No, wait. Before that, let's see the chapter, like the topics of the chapter. That is notions of work and kinetic energy. The work energy theorem. That is the first topic. Next topic is work. The chapter name is work, kinetic energy, work done by a variable force, the work energy theorem for a variable force, the concept of potential energy, the conservation of mechanical energy, the potential energy of a spring, power, collisions, and summary and points to ponder are some of the exercises, or just some points. Now let's start with the introduction. Introduction, introduction. The term work, energy, and power are frequently used. Okay, nice. The term work, energy, and power are frequently used in everyday language. We use work, these three terms, that is work, did you do any work? Energy, how much energy do you have? And power, are you very powerful? In our daily language, even though the physics is not the same, we do use them. A farmer plowing the field, a construction worker carrying bricks, a student studying for a competitive examination like us, and an artist painting a beautiful landscape. All are said to be working, but that is in our language terms. In physics, however, the word work covers a definite and precise meaning. Somebody who has the capacity to work for 14 to 16 hours a day is said to have a large stamina or energy. That is in language terms. We admire a long distance runner for his stamina or energy. Energy is thus our capacity to do work. In physics too, the term energy is related to work in this sense. The capacity to do work, we can say it is energy. But as said above, the term work itself is defined much more precisely. The word power is used in everyday life with different shades of meaning. In karate or boxing, we talk about powerful punches or kicks. These are delivered at a great speed. This shade of meaning is close to the meaning of the word power used in physics. We shall find that there is at best a loose correlation between the physical definitions and physiological pictures these terms generate in our minds. There is some relation between whatever we have in our minds based on our daily interactions and the actual physical terms. The aim of this chapter is to develop an understanding of these three physical quantities. Before we proceed to this task, we need to develop a mathematical prerequisite, namely the scalar product of two vectors. Before like we understand the three terms, of the important topic is scalar product. This is under the introduction itself. So let's see what the scalar product is. Scalar product. We have learnt about vectors and their use in chapter 3 physical quantities like displacement, velocity, acceleration, force, etc. Okay, our vectors. Examples for vectors are displacement, velocity, acceleration, force, etc. We have also learned how vectors are added or subtracted. we now need to know how vectors are multiplied. There are two ways of multiplying vectors, which we shall come across. One way, known as the scalar product, gives a scalar form two vectors, and the other known as the vector product produces a new vector from two vectors. Basically, in the previous chapter we saw how to add vectors or subtract vectors, but now in this chapter we are going to learn how to multiply vectors. Vectors can be multiplied two ways. The first way is known as scalar product. The second way is known as vector product. In the first way, scalar product, we multiply two vectors, and the result of that multiplication, we will get a scalar, that is a quantity that doesn't depend on direction. But in case of vector product, when we multiply two vectors, we will get a vector. As the name suggests, scalar product gives scalar quantity, vector product, the final result gives a vector quantity. That is what they're saying here. We shall look at the vector product in chapter 6. Here we are only going to see about scalar product. We will see vector product later. Here we take up the scalar product of two vectors. The scalar product or dot product, scalar product can be called as dot product, vector product can be called as cross product. The scalar product or dot product of any two vectors a and b, denoted as a dot b, is defined as a dot b, which is equals to ab cos theta. Okay, when there are two vectors, if for example there are two vectors a and b, and a vector dot b vector, which gives c vector, then magnitude of c vector, which is equals to ab, normal ab times cos theta, where cos theta, the theta is the angle between the two vectors a and b. A dot b and ab cos theta is equals to ab cos theta, where theta is the angle between the two vectors as shown in figure 5.a, wherever the figure is. Yes, this is the figure. The scalar product of two vectors ab is a scalar, ab cos theta. This is a vector, this is b vector, the angle between them is theta. Let's glance at the other diagrams as well. B cos theta is the projection of b onto a. B cos theta, basically this much is b cos theta, because we know that cos theta, which is equals to adjacent by hypotenuse. Hypotenuse in this case is b, so cos theta, which is equals to adjacent by b, where if we shift this side, we'll get b cos theta, which is equals to adjacent. So this distance will become b cos theta. And that in a fancy way of saying is that b cos theta is a projection of b onto a. The projection we see of b vector on a vector is called as b cos theta. Now this diagram, a cos theta, is the projection of a onto b. Same way, the projection of a onto b vector is called as a cos theta, similar to cos theta, which is equals to adjacent by hypotenuse. In this case, this is the adjacent, so that value by hypotenuse is a, so hypotenuse is a cos theta, which is equals to adjacent. Now let's come back here. A dot b, which is equals to ab cos theta, where theta is the angle between the two vectors as shown in the figure. Since a, b and cos theta are scalars, the dot product of ab is a scalar quantity. Each vector a, b has a direction, but their scalar product does not have a direction. We know that scalar product involves two vectors, but the product, finally the product we got a dot b, this can be c vector or whatever it might be. C, this will not be a vector. It's a mistake for showing that here. C here, a dot b will get, C is not a vector. It does not have a direction. It only has a magnitude. But A and B are vectors. They have a direction as well as magnitude. From equation 5.1a, that is this equation, we have a dot b which is equals to ab cos theta, which, since it's a scalar, we can also write as ba cos theta. Geometrically, b cos theta is the projection of b onto a in figure 5.1b, and a cos theta is the projection of a onto b in figure 5.1c. So a dot b is the product of magnitude of a and the component of b along a. Alternatively, it is a product of the magnitude of b to the and the component of a along b. Okay, they're saying that since we saw the figure here, this is the projection of b onto a. So basically, if we see this equation, when we write this as a bracket, we will get b cos theta, which is this one here. This is the projection of b onto a. When, if we see, this is the multiplication of a times the component of a or projection of b along a. Or when we take b outside and write a cos theta, it is same as saying the projection of b along the projection of b, right, a times the projection of b onto a, or b times the projection of a onto b. If that makes sense. Anyways, equation 5.1a shows that the scalar product follows the commutative law. We can say it's commutative law. It follows the commutative law. What is commutative law? That is a dot b which is equals to b dot a. This is the commutative law. If it is not equal, if a dot b is not equal to b dot a, in case of cross product we see that, or vector product we see that a dot b is not equal to b dot a. But in case of scalar product we can say a dot b which is equals to b dot a. So it follows the commutative law. Vector product doesn't follow the commutative law. Scalar product obeys the distributive law as well, meaning when if there is ab plus a times b plus c, we can write as ab plus ac. Or when there is a times lambda b, we can write as lambda ab, where lambda is a constant or a real number. Further, where lambda is a real number or constant. The proofs of the above equations are left to you as an exercise. How we can prove that? You should do it yourself. For unit vectors, I cap, j cap, k cap, we have, in case of scalar product, that is dot product, I cap dot I cap, j cap dot j cap, and k cap dot k cap, which is equals to 1. Why that is so? Because I cap cross, if we do, the angle between them is theta equals 0 and cos 0 which is equals to 1. So I dot I, that is I cap dot I cap, j cap dot j cap, and k cap dot k cap, all their angles between them is 0. So final answer is 1. But in case of I cap dot j cap, here since all the other axes are mutually perpendicular to each other, I dot either I cap dot j cap, j cap k cap, or k cap I cap all have theta equals 90 degrees, and cos 90 we know is 0. Given two vectors. Let's assume we are given two vectors, that is a which is equals to ax I cap plus ay j cap and az k cap, and b bx I cap by j cap and bz k cap. their scalar product is A dot B, which is given as AX, AX I cap, basically this one. When we multiply it, we get that since this one, if we multiply it this or this, since it's I cap times K cap or I cap times J cap, we will get it to be 0. So the only one that matters is when we multiply with Bx, and I cap it will become 1, so we'll get Ax Bx. And similarly, we will get Ay By plus Az Bz or Az Bz from the definition of the scalar product. And equation 5.1b, we have A dot A, which is equals to Ax plus Ay plus Az, or basically A square, which is equals to A square x plus A square y plus A square z. Since A dot A, which is equals to magnitude of A times magnitude of A times cos 0 is 1, so we can say scalar product of two vectors having same magnitude and same direction is equals to the direct product of those vectors, or basically A square, the square of the vector. If two vectors have same direction and same magnitude, they're basically the same vector. And next point is A dot B, which is equals to 0 if A and B are perpendicular, meaning cos 90 degrees is equals to 0. So if angle between them is 90 degree, meaning they are perpendicular, obviously they will be, the scalar product will be 0. Now they gave an example here, example 5.1. Find the angle between forces F, which is equals to 3 I cap plus 4 j cap minus 5 I cap unit, and displacement 5 I cap plus 4 j cap plus 3 k cap. Also find the projection of F on D, meaning F cos theta. They're asking we should find the angle between the force and displacement. Angle between force and displacement. Okay. Fine. F times t, which is equals to fx dx plus fy dy plus fz dz. We will get it as 16 units. And hence f dot d, which is equals to fd cos theta, and which is equals to 16 units. Fd cos theta, which is equals to 16 units. Now finding f square, that is fx square plus fy square plus fz square, we will get 9 plus 16 plus 25, that is 50 units, and d square as well 50 units. So cos theta, we will get it as base by hypotenuse, and base, which is 16 unit. Okay, we should draw the diagram here, it's much better. If this was the force vector and this was the displacement vector, then the resultant vector will be something like this: f and d, resultant f dot d. Wait a second, this is vectors that will not have direction. Okay, let's see what they did here. They took 16, that is the this value as adjacent side, by f times d. Okay, basically what they did is there is fd cos theta here. Okay, I will write it in word here. work, energy, and power. The chapter name, which is FD cos theta, which is equals to, we got it as 16 units. As for how we got that, we got that because FD, which is equals to F dot D, which is equals to Fx dx plus Fy dy plus Fz dz. That will get it as 16 units. Now both of these are equal. Otherwise, I can indeed do it once more. Fx dx plus Fy dy plus Fz dz. Now the vectors given, F vector, which is equals to 3i cap plus 4j cap minus 5k cap. 3i cap plus 4j cap minus 5k cap, and d vector, which is displacement vector, was given as 5 plus 4 plus 3. Oops. This is work, energy, and power. This is the formula. This is F dot D value, F, which is equals to this much, and D vector 5i cap plus 4j cap plus 3k cap. Okay, now solving it, we will get F dot D, which is equals to this formula here, where Fx, which is equals to 3 times 5, that is dx, plus Fy, that is 4 times 4 here as well, plus minus 5 times 3. This one and this one cancel, so F dot D, which is equals to 16 units. And we know that F dot D, which is equals to Fd cos theta. Therefore 16, which is equals to Fd cos theta. We found out value of F dot D. Substituting that value, Fd equals cos theta, and we know that we do not know F and D values. We know F dot F, which is equals to Fx plus Fy plus Fz, and same for D. We will get F square, that is F dot F, which is equals to 50, and F, which is equals to root 50. And after substituting all the values, we will get 50, and this will get force, which is equals to root 50. Now as for D square, which is D dot D, this as well we will get it at 50 after substituting values. D will get as root 50. Now we have both the values which we don't know from this equation. We'll get 16 equals root 50 times root 50 cos theta, which is equals to 16 by root 50 times root 50 cos theta, which is equals to 16 by root 50 whole square, is 50. And this one value, we do not know the value perfectly, but you will get value to be approximately 0.32 16 by 50 here after doing it. After doing the value, you will get as 0.32. That is 16 by 50. Where it has 0.32 and theta, which is equals to cos inverse of 0.32. That is the final value. Yes. Which is equals to 0.32 and theta, which is equals to cos inverse of 0.32. Okay. Now the next main topic, that is notions of work and kinetic energy, the work energy theorem. The following relation for rectilinear motion under constant acceleration alpha or a has been encountered in chapter 3. We know this equation basically, v square minus u square is equals to 2s, that is for rectilinear motion or linear motion, where u and v are initial and final velocities respectively, and s is the distance traversed. Multiplying both sides by m by 2, okay, we are multiplying both left hand side and right hand side by m by 2, that is mass by 2. We will get as half mv square minus half mu square, which is equals to mas, which is equals to ma. We know that, which is equals to, from laws of motion we know mass times acceleration, which is equals to force. So ma, which is equals to fs, where the last step follows from the Newton's second law, that this step basically. We can generate equation 5.2 to 3 dimensions by employing vectors. Okay, they're saying this is the equation we perform. Now this here, this acceleration and distance, these are both this vector, not vector, scalar quantities. But in the second case, we are considering all of them as vectors: velocities, acceleration, and displacement. Here they are speeds, acceleration, and distance. Here it is velocities, acceleration, and distance. Here A and D are acceleration and displacement vectors of the objects respectively. Once again, multiply both sides by m by 2. We obtain half mv square, half mu square is equals to ma times d, which is equals to force times or force F dot d. The above equation provides a motivation for the definitions of work and kinetic energy. The left side of the equation is the difference in the quantity half the mass times the square of the speed. Okay, they're saying that this basically what we see here is, this is a difference between a quantity, which you know it's kinetic energy based on the formula itself, the difference between kinetic energy, which is equals to force times or force dot displacement from its initial value to the final value. We call each of these quantities, this one, the kinetic energy, denoted by K or Ke. The right side of the product of the displacement and the component of the force along the displacement. The right side, which is force dot displacement, or we can say it as product of displacement and the component of force or force along the displacement, because we know the projections we saw earlier, as force was getting projected into the, I mean, A was getting projected onto B, the product of A getting projected onto B times B. In this case, the force getting projected onto displacement times displacement, or displacement getting projected onto force times force. This quantity, that is F dot D, is called as work or work done. It is denoted by W. Equation 5.2 is, then we can write this same equation as This one we know it's kinetic energy, and this one is displacement. So Kf, that is K final, kinetic energy final, minus kinetic energy initial, which is equals to work done, where K1 and K2 are respectively initial and final kinetic energies of the object. Work refers to the force and displacement over which it acts. Okay, they're saying work, whatever this work is, it refers to the force and the displacement over which it acts. Basically, the force that is acting with reference to the displacement, or the force acting per displacement, or not per displacement, for some displacement. The force causing displacement is called as work done. Work is done by a force on the body over a certain displacement. When a force is applied on a body, if there is a certain displacement, we call it as work done. Or we can, in other words of saying, another way of saying that is, work is done when force on a body is applied until there is a change in position, or which we call displacement. Equation 5.2 is also a special case of the work energy theorem. Equation 5.2 means this one. Wait, not that one. Yeah, this one only. This equation is a special case of the work energy theorem. V square minus U square is equals to AS, 2AS. That is a special case of the work energy theorem. The change in kinetic energy of a particle is equal to the work done by on it by the net force. This is the principle or statement of the work energy theorem. The work energy theorem states that the change in kinetic energy of a specific particle, which is equal to the work done on it by the net force. We shall generalize the above derivation to a varying force in later equation. Basically, they are saying the work energy theorem is basically delta K, which is equals to delta K, change in K is equals to work done. This is the main equation of the work energy theorem. That is K final minus K initial, which they have written here. Now let's see the example. Example 5.2. It is well known that a raindrop falls under the influence of the downward gravitational and the opposing resistive force. Okay, the force is acting on the raindrop falling down is the gravitational force and the air resistance. The latter, which is the the opposing force, is proportional to the speed of the drop, but is otherwise undetermined. Consider a drop of mass 1 gram falling from a height 1 kilometer. It hits the ground with a speed of 50 meter per second. Then what is the work done by the gravitational force? What is the work done by the unknown resistive force? Okay, the statement is when why water drop, like what kind of forces a water drop experiences when it's falling down. The raindrop will experience gravitational force and the resistive force, and this resistive force is directly proportional to the speed of the water drop. Higher the speed of the water drop, higher the resistive force. Gravity is not like that. Gravity depends on the mass, which is not going to change. If we assume a drop of 1 gram is falling from a height of 1 kilometer height, it's falling. It hits the ground, the final velocity is 50 meter per second. Then what is the work done by the gravitational force? Initial work done would be 0. So that is the reason let's see the answer. Answer, the change in kinetic energy of the drop is delta K, which is equals to K final minus K initial. K initial, the drop is starting from rest, so half mu square, u equals 0. This will also become 0, which will be Delta K is equals to half mv square. Half mv square, if we calculate, mass is 10 power minus 3, meaning 1 gram in terms of kg is 10 power minus 3 times velocity, which is in meter per second, so no need for conversion, which is mv square. So v square, so 50 times 50, we will get as 1.25 joule. The work done, or I mean the kinetic energy is generally represented in terms of joules, where we have assumed that the drop is initially at rest. That is what we have assumed, so that we will take initial velocity as 0. Assuming that g is constant with value of 10 meter per second square, the work done by the gravitational force, work done, which is equals to mgh, which is equal to 10 joule. This is basically the potential energy formula. The work done by the gravitational force, which will also be equal to the change in potential energy, that is mgh. Mgh, mass is 10 power minus 3, g gravitation, which is 10 power 10, and h, it is 10 power 3, so we'll get 10 joules as the final answer. And the change in kinetic energy is 1.25, whereas the work done by the gravitational force is 10 joule. So from the work energy theorem, the change in kinetic energy, which is equal to the total work done. So the total work done, the work done is done by two forces, that is gravitational force and the resistive force. If the work done by the resistive force on the raindrop, thus WR we need to find out. WR, which is equals to delta K minus WG. Here we will get 1.25 minus 10 minus 8.75 joule. That's the work done of the resistive force on the raindrop. Since it is against the direction of force or direction of motion, we take it as negative. Work, the next main topic is work. As seen earlier, work is related to force and the displacement over it which it acts. Consider a constant force F acting on an object of mass m. The object undergoes a displacement d in the positive x direction as shown. Okay, it's saying that whatever if there is a constant force F acting on the mass, like we are kind of applying a force on an object, it's having a mass of m, and due to that force, that object is having a kind of displacement. This is the object, we act a force like this, and there is a displacement in this direction, that is this much. Object undergoes displacement d under the influence of force, that is F. Then the work done by the force is defined to be the product of component of the force in the direction of displacement and the magnitude of this displacement. Okay, we are going to calculate the work done. What that statement means is that the force which is acting in this direction, the displacement which is in this direction, we take Fd cos theta. We can define it as the work done by a force is defined as the product of the magnitude of the force acting along the direction of displacement and the displacement. The product between displacement and the force are acting along the direction of the displacement. If we resolute this vector, resolution of this vector, F vector into this component, this is F cos theta, and this one which is F sin theta. This component F cos theta is acting along the direction of displacement, so this times this magnitude, we will get it as the work done. That is what the statement means. The work done by a force is defined to be the product of component of force in the direction of displacement and the magnitude of displacement. Thus W, which is equals to F cos theta d, is equals to F dot d. We see that if there is no displacement, there is no work done even if the force is very large. Meaning how much ever force you apply, if the object is not moving or it's not changing in position, there is no displacement, then the work done by you for applying that force is zero. Thus, when you push hard against a rigid brick wall, the force you exert on the wall does no work. Yet your muscles are alternatively contracting and relaxing, and the internal energy is being used up, and you do get tired. Thus, the meaning of work in physics is different from its usage in everyday language. Okay, what this means is when you push a large wall, a brick wall, no matter how hard you push it, you get tired, but there is no displacement of that wall. What that means is there is no work done because force into displacement. But if you ask, why do you get tired then when you are pushing something, even though it's not moving, you are getting tired? Why does that happen when there's no work done? Because your internal muscles when pushing that wall are contracting, relaxing, and there's a whole mechanism going on inside you, inside your muscles, that we do see in biology class 11, but I will not be going into that. Anyways, by because your muscles internally are doing changing, contracting and relaxing, the work, there is work done there, and you will get tired, but there is no work done by you on the wall. The work done, or in another way of understanding this is, there is work done, the work done by you on the wall is zero. That is what we can say. The total work done might not be zero, but the work that any kind of other work done might not be zero, but the work done on by you on this specific object, that is a wall, is zero. No work is done if the displacement, okay, fine, the cases where work done can be zero, that is, first case, the displacement is zero, as seen in the example above. A weightlifter holding a 50 kg mass steadily in his shoulder for 30 seconds does no work on the load during this time. This also same scenario. Basically, if displacement is zero, there is no work done. When there is a weightlifter holding a 150 kg mass steadily on his shoulder for 30 seconds or how much ever time, even for 100 years he holds also, there is no work done. The lifter did not do any kind of work done on that dumbbell or whatever it might be. But in his body there is work done. The force is the force is zero. The second case where work done is zero is since work done is equals to F times T or F dot D, when either displacement or force is zero, the work done will also be zero. A block moving on a smooth horizontal table is not acted upon by a horizontal force since there is no friction, but may undergo a large displacement. In case of an ideal world where it is a frictionless surface, if we just once we push it, the block will continue to move, slide down the frictionless surface. But there is no work acting on that. It's just moving because there is no opposing force. That is inertia, the first law of motion. But just because it's moving and having a very, very large displacement doesn't mean that there is work done. There is no work done there because there is no net force acting on it. The third case, the force and displacement are mutually perpendicular. This is so since theta equals pi by 2 and 90 degrees. Cos pi by 2 is equals to 0. For the block moving on a smooth horizontal table, the gravitational force mg does no work since it acts at right angles to the displacement. If we assume that the moon's orbit around the earth is perfectly circular, then the earth's gravitational force does no work. The moon's instantaneous displacement is tangential, while the Earth's force is radially inwards and theta equals pi by 2. Okay, what they're saying is the third case when work done is 0 is force we know is F dot D. I mean work done which we know is F dot D, which is basically FD cos theta. The third case, since it depends on cos theta as well, we know that cos 90 degree, which is equal to 0. So this theta, which can be 90 degree, is the angle between force and displacement. When the force and displacement, the angle between them is 90 degree, then as well the work done is 0. The examples given are when we are in a smooth surface, when we push something, it will go. There is no effect. Let's assume Earth, a similar kind of Earth, an ideal Earth, where there is no friction, or there is a table there. You push a block on that table because the gravitational force is acting towards the center, meaning it is perpendicular to the displacement. So there is no effect on the block's displacement, or even for a frictionless. It is better if we imagine a frictionless surface. Okay, the second example is the orbit between Earth and the Moon. I mean, the Moon's orbit around Earth. Since we know that the radius is always perpendicular to the tangent drawn on the circumference, the force will always be acting towards the center of the Earth. That is when we assume that the circular orbit, that is Moon's orbit around Earth, is perfectly ideally circular. Then the force acting on the Moon due to Earth's gravitational force will be 0, because theta is equals to pi by 2. Work can be both positive and negative. If theta is between 0 degree and 90 degree, cos theta in equation 5.4 is positive. If theta is 90 degree and 180 degree, cos is negative. Okay, they're saying work can be both positive and negative. How we can say work can be negative is if theta, which is between, we saw before resistive force that was minus 8.75 joule or something like that, the example we saw before. Why it can be negative is in the equation, that is fd cos theta, cos, it depends on cos, where if the cos is between, the theta is between 0 to 90 degrees, that is the first quadrant, all the values of the trigonometric functions will be positive. But as it goes from 90 to 180 degrees, or 0 to 180 degrees, at the second quadrant cos is negative. So in that case, where cos 180 degree, if we take cos 180 degree is minus 1. So minus 1 times fd, which is equals to f minus fd. So the work done will become negative. In many examples, the frictional force opposes the displacement, and theta, which is equals to 180 degrees. The work done, which is equals to negative, that is minus 1. Frictional force is acting always, most of the cases, frictional force acts as opposes the motion. So the angle between displacement and the frictional force will most likely be 180 degrees. So in such a case, the work done by friction, which is also a force, which is equals to negative. From equation 5.4, it is clear that the work and energy have same directions, same dimensions. Equation, basically they're saying delta k, which is equals to work done, which is delta k, which is energy, which is equal to work done. From this equation, we are clear that both the kinetic energy or energy have and work done both have same dimensions. This is we learned from the measurements, units and measurement chapter, where we know that when there is an equation like this and it's a correct equation, then the homogeneous, basically it means both of them have same dimensions, that is ml square t power minus 2. The SI unit of this is joule, named after the famous British physicist James Prescott Joule, or Joule, 1811 to 1869. The work done is named after a famous British physicist that is James Prescott Joule or Joule. And since work and energy are so widely used as physical concepts, alternative units abound, and some of these are listed in 5.1, table 5.1. Okay, since this and work and energy are like language, we use it in language in the actual communication interactions and such. There are many kinds of units, not only joules. So alternative units of work energy in joule, since work and energy have the same dimensional formula, work and energy have the same units, SI unit, that is joule. Other units are ergs, that is 10 power minus 7 joule. 1 erg, which is equal to 10 power minus 7 joule. Electron volt, which is equal to 1.6 into 10 power minus 19 joule. Basically, electron volt is defined as when an electron is accelerated through a potential difference of 1 volt, the work done on that electron is 1 electron volt. Okay, anyways, calorie, this is 4.186 joule. The energy we get from a calorie is 4.186 joule. Kilowatt hour, that is our current unit. We call it as units here, and it is which is equal to 3.6 into 10 power 6 joule. Now let's see the answer. I mean the example. A cyclist comes to a skidding stop in 10 meters. During this process, the force on the cycle due to the road is 200 Newton and is directly opposed to motion. The first question is, how much work does the road do on the cycle? Second question, how much work does a cycle do on the road? Okay, they're asking, they're saying that a cyclist, the one who is riding a cycle, he comes to a skidding stop, meaning he brakes, and after 10 meters he stops, meaning there's no rolling motion. The tires completely stopped, both the tires stopped. The stopping distance is 10 meter, and during this process, when there is this much process like the skidding process, the friction or the force on the cycle due to the rotor, this is frictional force, which is equals to 200 Newton, and this is directly opposing the motion. With this 200 frictional force, which we know which is equals to, for kinetic friction, this is kinetic friction from previous chapter, we know the frictional force is equals to mu k times n. And they're asking how much work does a road do on the cycle and how much work does a cycle do on the road. Work done on the cycle by the road is the work done by the stopping frictional force on the cycle due to the road. Basically, they're saying both is the same. Both are same thing according to Newton's third law. Both are equal and equal and opposite. The first thing they ask, the stopping force and the displacement make an angle of 180 degree. We know it's a frictional force makes 180 degree angle. We saw an example before, or a statement before. 180 degrees, or basically pi radians with each other. Thus, work done by the rod is equals to FD cos theta, force which is 200 newtons, distance which is 10 meters, and cos pi or cos 180 degrees, which is equals to minus 1, totally minus 2000 joules of work done. It is the negative work done that brings the cycle to a halt in accordance with the work energy theorem. From Newton's third law, an equal and opposite force acts on the rod due to the cycle. Its magnitude is 200 Newton. However, the rod undergoes no displacement. Thus, work done by the cycle on the road is zero. Basically, according to Newton's third law, the force on the road by the cycle, which is same as the force on cycle due to road, which is 200 Newton. But since road is not going away or moving, there is no displacement. And when there is no displacement, the work done is zero. The lesson of example 5.3 is that though the force on a body A exerted by the body E, body B is also equal and opposite to that of B by A, the work done on A by B is not necessarily equal and opposite to the work done on B by A. Okay, this is what we saw in the example. Basically, this is the statement of why the work done on the road is zero. They're saying that if there are two bodies A and B, according to Newton's third law, the force on body A due to body B is equals to force on body B by body A. They are equal and opposite. But that does not mean the work done also is equal and opposite in the both bodies. That is not necessarily true. Now let's go to the next main topic, that is kinetic energy here. Kinetic energy, as noted earlier, if an object of mass m has velocity v, its kinetic energy k, which is equals to half mv square. Since we take it, since velocity is a vector, v dot v, which is equals to v dot v, that is v square cos theta. Since the angle between them is 0, cos 0 is equals to 1, we can directly write it as v square. So kinetic energy is equal to half mv square. Kinetic energy, which we got from a vector product of two velocity vectors. Kinetic energy is a scalar quantity. The kinetic energy of kinetic energy, work done, both are scalar quantities. This kinetic energy is a scalar quantity. The kinetic energy of an object is a measure of the work done. Is a measure of the work on a object can do by the virtue of its motion. Okay, basically what this kinetic energy is, the kinetic energy of an object is a measure of the work an object can do by the virtue of its motion. If an object is moving, that is, it is in motion, the amount of work done by this moving object is called as kinetic energy, is measured in terms of kinetic energy. There is typical kinetic energy scale, that is how much kinetic energy for reference. Assuming car, let's assume it's a car. If the mass is around 2000 kg and speed is around 25 meter per second, the kinetic energy, which is in joule, is 6.3 into 10 power 5. If maybe, anyways, a running athlete, mass ideally 70 kg, speed which is 10 meter per second, and from our formula we'll get 3.5 into 10 power 3 joule, which is the velocity, the kinetic energy. Bullet, 5 into 10 power minus 2, 200 is the speed, 10 power 3 energy, meaning when you shoot a bullet through a gun and it pierces a wall, if the bullet was immediately stopped, then a total of 10 power 3, or it was not immediately stopped, like it came to a stop after some distance or whatever it might be, the work done by the bullet on the wall, which is equals to 10 power 3 joule, because it came to stop, that is change in kinetic energy. As for if there is a confusion as to why a running athlete having a little more energy than a bullet can't go through a wall, as a bullet did. That is because area, the bullet concentrates all its force, that is in a single point area, or work done on a single, the bullet does work done in a single point, whereas the athlete cannot do that. Stone dropped from 10 meters. If the stone is 1 kg in mass, is a very heavy stone. Speed, which is 14 meter per second, that might be the final speed. The work done is 10 square joule. Raindrop at terminal speed, meaning very close to the ground. Mass 3.5 to 10 power minus 5 kg. Speed 9. So the work done is very less, 1.4 into 10 power minus 3. An air molecule, which is very, very small and very, very less weight, 10 power minus 26 grams, has a speed of 500 grams and does a work of approximately 10 into 10 power minus 21. Okay, let's see the statement of kinetic energy again. Kinetic energy is an object, is a measure of the work done an object can do by the virtue of its motion. This notion has been intuitively known for a long time. The kinetic energy of a fast-flowing stream has been used to grind corn. Sailing ships employ the kinetic energy of the wind. Table lists the kinetic energies for various objects. Okay. The flowing stream which has kinetic energy, the wind which has kinetic energy, which we use them to do many kinds of works. Now, anyways, there's an example here. In a ballistics demonstration, a police officer fires a bullet of mass 50 grams with speed 200 meters per second on a soft plywood of thickness 2 centimeter. The bullet emerges with only 10% of its initial kinetic energy. What is the emergent speed of the bullet? Okay, they are saying that in a guns or a ballistics demonstration, a police officer fires a bullet of mass 50 grams. The mass of the bullet is 50 grams, which is 5 into 10 power minus 2 kg. This bullet has an initial speed of 200 meter per second, and it is pierced into a plywood of 2 centimeter thickness. After that, the final kinetic energy after piercing through this plywood is 10% of its initial kinetic energy. Then what will be the speed of the bullet? Okay, V final they're asking. Fine, let's find, we know that work done which is equals to delta Ke, which is equals to work done, the initial kinetic energy of the bullet, which is equals to 1000 joule. It has a kinetic energy of, it has a final kinetic energy of 100 joule. They say it's 10% only, so the final is 100 joule. If Vf is the emergent speed, then half mu square, or yes, half mv square, v final velocity square, which is equals to 100 joule, that is what they said. Vf, which will get us 2 into 100 by 0.05 whole root, or whole power by 2, 1 by 2. The speed will get us 63.2 meter per second. The speed is reduced by approximately 68%, not 90%. When kinetic energy was reduced by 90%, the speed only reduced by 68%. We would assume it would reduce by 90%, but that was not the case. Work done by a variable force. A constant force is rare. Okay, the next main topic is work done by a variable force. In nature, in the real world, a constant force is very rare. It is a variable force which is more commonly encountered. Figure 5.3, which is 5.3a here, is a plot of varying force in one dimension, acting only in one direction, either x-axis, y-axis, or z-axis, only in one direction. There is a force like this. There's force per displacement. At one displacement, it's acting this way. At another, it increased. At another displacement, it increased even more. And this area, this rectangles here, this area is force times displacement, so it will give the area of this graph here will give us the work done by the force. If the displacement delta x is very small, we can take the force f of x, which is approximately constant, and the work done is then delta w is equals to f of x times dx, or delta x. This, the shaded region, this one, this figure here, the shaded region rectangle represents the work done by the varying force of x over the small displacement delta x, which is equals to f of x times dx. This diagram here, this is a B diagram. The adding the areas of all the rectangles, we find that delta x, which is reaching to 0, the area under the curve, is exactly equal to the work done by f of x, the force acting along the x direction, or the displacement direction. Basically, after integrating this equation here, which is delta w is equals to f of x times d of x, you will get the total work done. Okay, let's see the example. A woman pushes a trunk on a railway platform which has a rough surface. She applies a force of 100 newtons over a distance of 10 meters. Thereafter, she gets progressively tired and her applied force reduces linearly with distance to 50 meters. The total distance through which the trunk has been moved is 20 meters. Plot the force applied by the woman and the frictionless force, the frictional force, which is 50 Newton versus displacement. Calculate the work done by the forces over 20 meters. They're saying there is a woman who is pushing a trunk in a railway station or a railway platform. There is a trunk, she's pushing that, and she's applying a force of 100 Newton, that is over 10 meters. She's applying a constant force of 100 Newton over 10 meters. But she gets tired. After some time, she gets tired. And her applied force from 100 Newton decreases to 50 Newton. That is not with like at 1 second it was not 100 and other it was not 50. It decreased from 100 to 98, 100 to 70, 100 to 60, 100 to finally 50. The total distance through which the trunk has been moved is 20 meter. First 10 meter with 100 Newton and another 10 meter with 50, in between speeds. No, forces. Plot the force applied by the woman and the frictional force, which is 50 Newton, versus the displacement. Calculate the work done by the forces. Okay. This is the graph here. Graph Fn, force basically per displacement, that is 20 meter here till 10 meter mark there is a constant force of 100 Newton, and for the next 10 meters it is decreasing till reaching 50 at 20 meter mark. Plot of the force F applied by the woman and the opposing frictional force F versus displacement. The plot of the applied force is shown in figure 5.4 at x equals 20, force which is equals to 50 Newton, not 0. We are given that the frictional force F, which is equal to 50 Newton, it opposes motion and acts in a direction opposite to F. It is therefore shown on the negative side of the force axis. The work done by the woman is area of the rectangle ABCD plus area of the trapezium CID. Work done, which is equals to 100 times 100 times 10, that is 10 meters times 100 Newton force, plus the trapezium, which is half times the sum of the parallel sides times the perpendicular distance between them. So we'll get half times 100 plus 50 times 10. Finally, the answer we will get as 1750 joules, the work done by the woman. Then work done by the frictional force, that is the below graph. This one, the frictional force has always been acting. It's minus 50 Newton. So this force has always been acting. The work done by the frictional force, which is equals to area of the triangle AGHI, that is the below triangle, this one here, shaded here like this, which is equals to minus 50 times 20, which is equals to minus 1000 joules. The area on the negative side of the force axis as a negative sign. Now let's come to the next main topic, the work energy theorem for a variable force. Before we saw the constant force, now for a variable force. We are now very familiar with the concepts of work and kinetic energy to prove the work energy theorem for a variable force. We confine ourselves to a one dimension, the time rate of change of kinetic energies. This, whatever we are doing right now, is only for a single dimension, and the time rate of change of kinetic energy, basically the rate of change of kinetic energy, dk by dt, is equals to half mv square changing with respect to dt. Now we know that from when we substitute it, we can write it as, we know half is constant, so no need to write it, and you will get mass, which is equals to dv by dt, and dv by dt, which we know is acceleration, and mass times acceleration, here we will get force, that is from Newton's second law. Force times velocity, one v is left out because there's a v square, so dk by dt is equals to force times velocity. Velocity we can write as dx by dt, and here there is dk by dt, so dt cancel, we will get finally dk, the change or the small change in kinetic energy, which is equals to force times the small change in displacement. Integrating the initial position x1 to the final position xf, we have where we have integrating, we will get dk from k initial to k final, and f dx, which we will get from x1 to, or x initial to x final, where k1 and ki and kf are the initial and final kinetic energies corresponding to ki and kf. We will get kf minus ki, that is after integration, which is the final integration of f dx. From equation 5.7, we know that kf minus ki delta k, which is equals to w, thus the WE theorem is proved for a variable force. This is the variable force here. This is the variable force normally we can take it outside if it was constant, but we cannot take it outside when it is variable, so we keep it inside the integration k final minus k initial, which is equals to variable force times dx, or with respect to dx, whole integration from x initial the change in force from x initial to x final. And thus we have proved for a WE theorem, work energy theorem, for a variable force. How we did that is we took kinetic energy formula, that is half mv square. We took it with respect to time. Then we got m dv by dt times v. dv by dt is acceleration, mass times acceleration is force. Force times velocity, which is equals to dx by dt. Dx cancel, we will get dk, which is equals to f dx. While the work energy theorem is useful in a variety of problems, it does not, in general, incorporate the complete dynamical information of Newton's second law. Okay, it is a kind of integral form of Newton's second law. Newton's second law is the relation between acceleration and force at any instant of time. Okay, basically this WE theorem, that is work energy theorem, we saw v square minus u square is equals to 2s. This is the rectilinear motion laws, or the equations of motion. This was another form of the simplified form of work energy theorem. This work energy theorem is one more form of Newton's second law. This Newton's second law is the relation between acceleration and force at any instant of time, that is work energy theorem. I mean, not integral form of the Newton's second law is work energy theorem. Integral form of Newton's second law. Newton's second law is relation between acceleration and force at any instant of time. Work energy theorem involves an integral over an interval of time. Here, instead of the interval of time, we take an integral. That is why it's an integral form of Newton's second law. In this sense, the temporal, meaning time, information contained in the statement of Newton's second law is integrated over and is not available explicitly. Another observation is that Newton's second law for 2 or 3 dimensions is in vector form, where the work energy theorem is in scalar form. In scalar form, information with respect to direction contained in Newton's second law is not present. Okay, basically they're saying that the time information, that is temporal information present in the Newton's second law, the disadvantage of work energy theorem they're saying here, that is the time information here, it's just integrated over here in case of work energy theorem. After integration we get to work energy theorem. Time information is not explicitly there, not available in the work energy theorem. And observation is that, like, in Newton's second law, which is force equals mass into displacement, or force which is equals to change in momentum per unit time, they all are vectors. So in a three-dimensional world, it will still retain its direction. But in case of work energy theorem, which is a scalar, it will not be retained, or it will not have a direction in the vector form. It will only be in the scalar form. In the scalar form, information with which directions acting and all won't work. With respect to directions contained in Newton's second law is not present. Now that is what I said. Now let's go to the example here. A block of mass 1 kg moving on a horizontal surface with speed v final, which is 2 meters per second, enters a rough patch ranging from x equals 0.10 meter to x equals 2.01 meter. The retarding force Fi on the block in this range is inversely proportional to x over this range. Okay, they're saying that there is a block of mass m. The mass of the block is m. It is 1 kg. The mass of the block is 1 kg, not m. It is 1 kg. It is moving with a horizontal speed, that is 2 meters per second. It is entering a rough patch ranging from x, that is the coordinates here, 0.1 to 2.01. The retarding force F1 on the block in this range is inversely proportional to the x over this range, meaning the force increases, or the roughness of the ground increases as the distance, the coordinate from x 0.1 to 2.01 increases. Fr, that is equals to minus k by x for 0. Basically, they gave that force is directly inversely proportional to x. They added a constant which is equals to k by x. But since we know frictional force is negative, so force which is minus k by x, that is what they gave here. Or it might not be visible. Just same thing I wrote again. So R, which is a frictional force, which is equals to minus k by x for 0.1, which is smaller than x, and 2.1, which is smaller than, I mean, greater than 2. X is smaller than 2.1 and greater than 0.1, equals 0. The frictional force is 0 when x is like lesser than 0, when it is the rough patch is introduced from 0.1 only. Before that, there is no rough patch. It's a frictionless surface. So at that time, the frictionless force is 0. And like at x, after this 2.01 meter, where k which is equals to 0.5 pi joules, what is final kinetic energy and Vf of the block as it crosses this patch? They're saying that a block is moving from some distance where there's a rough patch. There is friction introduced. The friction is varying as the distance increases. Friction also increases, meaning as it goes from the initial, it's not a constant friction, as the roughness of the surface increases as the block travels. And after some time, the friction will become 0. That is after crossing this 2.01 meter mark. Where initial kinetic energy, they gave it as 0.5 joule, and this is V final they gave. V final, that is 2 meter per second. They did not give V initial velocity. The initial velocity of the, wait, this is V initial itself. Wait. V initial, which is 2 meter per second. We should calculate the final kinetic energy as well as the final velocity of the block from equation 5.8a, that is the integral equation. We know that change in kinetic energy, which is equals to force dx, force they have it as minus k by x. K is a proportionality constant, so we have 1 by x with respect to dx. When we integrate 1 by x with respect to ds, we will get ln x, ln of x, which is from 2.01 to 01, so we'll get ln of 2, that is 2.303 into log of 2. Log of 2 is 0.31. We'll get 0.693 into minus k, that is half mv initial square minus k into 0.693. Wait a second. Okay, okay. This is not what they did here is, I will solve the question with, of course, the blueprint. That became an oval. Wait, I forgot to change it. Yes. Example, they gave that given mass of block is equals to 1 kg. Initial velocity which is equals to 2 meter per second. Frictional force F friction is equals to minus K by X. And change in displacement, that delta X, which is equals to 2.01. Okay, let's keep it like that for now, where X initial, which is okay, fine. From before we saw that the change in kinetic energy Kf minus Ki is equals to, this is a variable force 1, integration from initial xi to x final force times dx, or with respect to dx. In this case, we know this value, force we know, so substitute K final minus K initial, that is K final. They asked us to calculate K final, so I do not know. K initial, it is half m u square is equals to xi xf minus k by x dx, kf which is equals to minus half m1 v2 square, so it is 2, right? Yes, initial velocity was in it given to be 2 meter per second, so which is equals to minus k is constant, so it is minus k xi x f 1 by x dx, kf minus 2 is equals to, this is not kinetic energy, this is a proportionality constant, and differentiation with respect to dx, that is 1 by x with respect to dx, which is ln of x from x initial to x final, and x initial which is equal to 0.1, x final which is equals to 2.01, so that is basically kf minus 2 which is equals to minus k ln of 2.01 minus ln of 0.1. We can write this as minus k times of ln of 2.01 by 0.1, and kf minus 2 is equals to minus k, there is multiplication here, we can write this 2.303 log of 0.1, we can write as 20.1. Ln of anything can be converted into 2.303 into log of 20.1, or 20 point this I multiplied 0 ones are into 20.1, converting ln into log, we multiply by 2.303. We need to know the value of log, that we can find from the log table, and we will get k final which is equals to this final value. Here if we see the same thing they did here, ln minus ln of that, we will get 2 minus 0.5 into ln of 20.1. Ln of 20.1, they got the value as 1.5, and we will get joule is equals to 0.5 joule. And if that was the case, we know half mv square equation from that 0.5 joule. So we will get it as velocity, final velocity 2 kf by m whole root. We will get it as approximately 1 meter per second. Here note that in a ln is a symbol for natural logarithm to be to the base of e, and not the logarithm to the base of 10. Ln x, which is equals to log ex, is equals to 2.303 log of x, log of base 10x. Okay, that was that. Now let's go to the next question. Concept of potential energy. The word potential suggests the possibility or capacity of action. That is the meaning of potential word. This potential word here means that possibility of action or capacity of action. I'll be taking, before starting the potential topic, I'll be taking a 5-minute break. Okay, then let's start. The break was a little longer than expected. Anyways, the next main topic, that is concept of potential energy. The concept of potential energy. The word potential suggests possibility or action of capacity, or capacity for action. They're saying that no, we know that potential suggests, like what this potential means, that the potential means the possibility or capacity for the action. The term potential energy brings to one's mind stored energy. Like if we hear potential energy, it means that it is stored energy. A stretched bowstring possesses potential energy. When you stretch a bowstring, it will possess some potential energy. When it is released, when we release the bowstring, the arrow flies off at a great speed. The Earth's crust is not uniform, but has discontinuities and dislocations that are called fault lines. These fault lines in the Earth's crust are like compressed springs. They possess a large amount of potential energy. An earthquake results when these fault lines readjust. There is a new concept. It's not a concept, it's just a fact. They're saying that potential energy is a kind of a stored energy. Example is when you stretch a string, a bowstring, and when you release the bowstring, the arrow will fly at great speeds. And the arrow flies off at a great speed. And in Earth's crust, the Earth's crust is not uniform. There are many discontinuous and dissociations. These dissociation and discontinuities are called as fault lines. These fault lines in the Earth's crust possess enormous amount of potential energy. These act as compressed springs. When there is an earthquake, this results in the readjustment of these fault lines. That's why there is an energy release. Thus, potential energy is a stored energy by virtue of its position or configuration of a body. In string, when we pull the string, that configuration of the pulled string gives stores the potential energy in that string. In case of Earth, the configuration of the fault lines which stores the potential energy. The body left to itself releases the stored energy in the form of kinetic energy. When the body is left to itself, after you release the string, it will release the stored energy. In the form, this potential energy gets converted into kinetic energy. That is what it means by this stored energy is released in the form of potential energy. Let us make our notion of potential energy more concrete, more understandable. Gravitational force on a ball of mass m is mg. The gravitational force on a ball of mass m is mg. G may be treated as a constant near the Earth's surface. By near, we imply that the height of h of the ball is very small compared to Earth's radius. Very, very small. So that we can ignore the variation of g, that is acceleration due to gravity, near the Earth's surface. They gave a star mark. There is a note point. The variation with gravity with height is discussed in gravitational chapter. That is chapter 7. Okay. The gravitational force on a ball of mass m is mg. This is constant near Earth's surface. So that we can, this is not the main point. In what follows, we have taken the upward direction to be positive. Let us raise the ball up to a height h. Okay, there is a ball, we are holding a ball. Let's consider like the upward direction as positive direction. When we when we rise the ball up, we're lifting the ball up or a dumbbell up. The work done by the external force or us for lifting the ball against or dumbbell against the gravitational force that is mgh. The work we are doing is stored in the form of potential energy, that is mgh. This work gets stored as potential energy. Gravitational potential energy of an object as a function of height is denoted by v of h. Basically, they're saying that the gravitational potential energy of an object as a function of height h is denoted by v of h, and it is negative of work done by gravitational force in rising the object to that height. V of h, which is dependent on the height, is equals to mgh. If h is taken as a variable, it is easily seen that the gravitational force F equals a negative of the derivative Fh with respect to h. Thus, F, which is equals to minus dv of h by dh, equals to minus mg. The negative sign indicates that the gravitational force is downward. When released, the ball comes down with an increasing speed. Just before it hits the ground, its speed is given by the kinematic relation v squares is equals to 2gh. This can also be written as half mv square mgh by multiplying with half and half m, which shows that the gravitational potential energy of the object at height h and the object is released manifests itself as kinetic energy of the object on reaching the ground. When we lifted it, the work done, the potential energy, the work done we did for lifting the ball up or dumbbell up was stored as potential energy, and when we release it, the ball falls down. This is the ball attaining kinetic energy. That is what they're saying. Physically, the notion of potential energy is applicable only to the classes of forces where work done against the force gets stored up as energy. When external force constraints are removed, it manifests itself as kinetic energy. Okay, they're saying that this physically the notion of potential energy is applicable like only when the work we done, the force where work done against the force, only if that gets stored up is there a potential. If it doesn't get stored up, there is no potential energy. After it is the constraints which are like us holding the ball up, we remove the hand, the constraint is removed, the potential energy is released, it falls down. There is nothing like stopping the, if there is no one stopping the potential energy from getting released, it will get transferred or transformed into kinetic energy, manifests itself as kinetic energy. Mathematically, in case of one dimension, the potential energy V of x is defined for the force f of x can be written as f of x, which is equals to minus dv by dx, where dv is the change in potential, small change in potential energy, dx is the small change in displacement. Basically, force into displacement is equals to work done, same equation. Sometimes it can be potential energy, and that is the force, which is equals to minus dv by dx. This implies that when we do differentiation here, we get that the change in potential energy, which is equals to, for a variable force that is dependent on the x, which is a function force of x, force f of x with respect to dx. After integration, we will get the change in potential energy. The work done by a conservative force such as gravity depends on the initial and final positions only. Because there are conservative and non-conservative forces, the forces which does not depend on path are called as conservative forces, and which depends on path followed are called as non-conservative forces. In the previous chapter, we have worked with examples dealing with inclined planes. If an object of mass m is released from rest from the top of a smooth frictionless inclined plane of height h, its speed at the bottom is root 2 GH irrespective of the angle of inclination. Okay, they're saying that if an object of mass m is released from rest from top of a smooth frictionless surface, inclined plane of height h, its speed at the bottom is root 2 GH irrespective of the angle of inclination. This is a point to be remembered. Thus, at the bottom of the inclined plane, it acquires a kinetic energy mgh. With the work done, or the kinetic energy did depend on other factors such as velocity or particular path taken by the object, the force would be called non-conservative. That is what I said, definitions of conservative and non-conservative. Like example, how we know it is conservative force, it does not depend on path taken. The speed finally, like when we take an inclined plane, the displacement from, fine, I will do it, explain it. This is our previous problem. Now let's assume gravitational potential energy. This is position A, and this is somewhere here, this is position B. There is some distance h between them. The work done for a ball like this to go from here to here will be, like, if let's assume here it is conservative, the gravitational potential energy earth, so there is some force. If it is m, the force is mg, and the work done for moving this force, work done is equals to mgh. And the final velocity, let's assume the final velocity vf, which is some 10 meter per second or something like that. Now let's take one more case. Same earth. Now let's take an inclined plane. Now this angle is theta, this position is A, this position is B, or then if a ball is rolled down here again at this position, the velocity, since both are same points, let's assume the distance, same distance h, here also when the ball roll down like this, the final velocity will be equal to 10 meter per second. That is, and this is frictionless surface, only frictionless surface. That is what they mean by conservative force. That is the reason why gravitational force is conservative force, and conservative forces do not depend on path followed. Anyways, now the dimensions of potential energy are ml square t power minus 2, same as energy, same as work done, and unit is same as them as well, joule. the same as kinetic energy or work. To reiterate, the change in potential energy for a conservative force delta V is equal to the negative of work done by the force delta V, which is equal to change in potential energy, which is equals to minus f of x times delta x. In the example of a falling ball considered in this section, we saw how potential energy was converted to kinetic energy. This hints at an important principle of conservation in mechanics, which we now proceed to examine. The next main topic, that is conservation of mechanical energy. For simplicity, we demonstrate this important principle for one-dimensional motion. Suppose that a body undergoes displacement delta x under the activation of an conservative force F. Then from the WE theorem, work energy theorem, we say that change in kinetic energy, which is F of x times delta x. Okay, let's assume a body is there, it's undergoing some displacement due to a conservative force F. Then from work energy theorem, we say that the change in kinetic energy of that body, which is equals to F of x, or force times displacement basically. If this force is conservative, the potential energy, that is V of x, can be defined as minus delta V, the change, negative or change in potential energy, which is equals to force into displacement. The above equations imply that delta K plus delta V, which is equals to 0, so the change in total energy is equals to 0. Okay, what that means is, since we are moving an object due to a force, if there is a force, there is an acceleration. There's an acceleration, due to the acceleration, the velocity increases. So kinetic energy also increases. There is an increase in kinetic energy. That is why we see a change in kinetic energy here. And what about potential energy? Potential energy is negative of the work done. Okay, there is a loss of potential energy, meaning here V initial minus V final is loss of work done. That is what we get here. Since we get V final minus V initial is negative, so that means the initial potential energy is higher than the final potential energy. Meaning, in case of mm, a ball or a dumbbell which we take up, if we take the ball up, the potential energy is more, but the kinetic energy is 0. As the ball, we leave that ball down, the potential energy decreases, and kinetic energy slowly increases. This goes on until kinetic energy is maximum, potential energy is 0. That is what happens. That is why as the displacement increases, here the potential energy decreases. And since we can write delta V, which is equals to minus F of x delta x, now if we add both kinetic energy and potential energy, delta k plus delta V, which is equals to f of x delta x minus f of x delta x. Cancel, we will get that delta k plus delta V, which is equals to 0. And delta, the change, if we take out common, we will get that the total change in kinetic or potential energy, or basically the total energy, when we add kinetic energy and potential energy, we get the total energy of the particle. The change in total energy of the particle will always remain 0. This is because of the conservation of mechanical energy theorem. Energy can neither be created nor be destroyed. So the total energy of the system will never be changed or will always be 0. It can only transform from kinetic to potential and potential to kinetic, which means that K plus V, the sum of kinetic and potential energy of the body, is a constant over the path x initial to x final, no matter which path that is. This means that K initial plus potential energy final, initial, K initial initial kinetic energy and initial potential energy, the sum of initial potential energy and initial kinetic energy is equal to the sum of final potential energy and final kinetic energy. If there is no, if this is for a single system, for an isolated system or something like that, since it will always be, it will not change, we can say initial equals to final, conservation of energy. The quantity k plus, I mean kinetic energy, and plus the sum of kinetic energy and potential energy is called the total mechanical energy of the system. Individually, the kinetic energy k and the potential energy v of x may vary from point to point, but the sum is a constant. The aptness of the term conservative force is now clear. There is one more reason we call it as a conservative force, because it is conserved. Let us consider some of the definitions of a conservative force. Definitions of a conservative force. A force f of x is conservative if it can be derived from a scalar quantity v of x, that is potential energy, by the relation given by equation 5.9. That is which one? Yes, wait. This one. Delta h is equals to minus f of x delta x. A force is conservative if it is can be derived from this equation by relation. The three-dimensional generalization requires the use of a vector derivative, which is outside the scope of this book. Like, we can derive it three-dimensionally, but it's not needed, and it is not needed for us. The work done by conservative force depends on the endpoints. This can be seen from the relation W, which is equals to kf minus k initial, which is equals to v of x initial minus v of x final, or minus of v of x final minus v of x initial. Just applying the minus inside, we will get the terms reversed, which depends on the end positions. A third definition states that the work done by this force in a closed path is zero. This is once again apparent from the equation 5.11, since x initial, which is equals to x final, meaning when displacement is zero, wherein x, the initial and final position is same, displacement is zero, the work done in that case is zero. Okay, how we can define a conservative force is that the first point, it should be derived from this equation. It should be able to be derived from this equation. That is the first requirement. Second requirement, this work done should only depend on the initial and final point, not the path followed. And the third point, if there is no change in position, there is no work done. Thus, the principle of conservation of total mechanical energy can be stated as the total mechanical energy of a system is conserved if the forces doing work on it are conservative. The total mechanical energy of a system is conserved if forces doing work on it are conservative. The above discussions can be made more concrete by understanding an example of the gravitational force once again, and that of spring force in the next section. 5.5, the figure 5.5 depicts a ball of mass m being dropped from a cliff of height h. This is a cliff. We drop a ball here, initial velocity is 0. At height h, it is vh. At just before touching the ground, it is vf. The total height of the cliff is h, capital H. The conservation of potential energy to kinetic energy for a ball of mass m dropped from height h. The total mechanical energies E naught, E small h, and E capital H of the ball at the indicated heights are 0, that is at the initial E naught, and H and capital H. EH, the total is equals to mgh, and E small h is equals to mgh plus half mv square, as total energy is equal to sum of kinetic energy and potential energy. At the ground level, there is no kinetic energy. At the start level, there is no kinetic energy. So there is only half mv square and only mgh here. The constant force is a special case of spatially dependent force f of x, as the mechanical energy is conserved. Thus, the final energy, which is equals to the initial energy. Hence, mgh, which is equals to half mvf square. So Vf is equals to root 2 gh. As a result, that was obtained in section 5.7 for a free falling body. Further, Eh, which is equals to E small h, which implies V square h, which is equals to 2g times h minus h, and is a familiar result from kinematics. At the height h, the energy is purely potential. It is partially converted to kinetic energy at small h and is fully kinetic at the ground level. This illustrates the conservation of mechanical energy. Okay, there is a example given here. Let's see the example. A bob of mass m is suspended by a light string of length L. It is imparted a horizontal velocity Va, no V naught, at the lowest point A, such that it completes a semicircular trajectory in the vertical plane with the string becoming slack only on reaching the topmost point C. This is shown in figure 5.6. Obtain an expression for V naught, the speeds at point B and C. 3. The ratio of the kinetic energies at B and C. Comment on the nature of the trajectory of the bob after it reaches the point C. Okay, they're saying that there is a bob of mass m. It is suspended by a string. Basically, you tied a ball or something like that to the end of a string. After that, you just left it like this. And then you started spinning it. You imparted a velocity to that bob. At the lowest point, that is a point here, that is the lowest point, there is a velocity v naught, and this velocity, it allows the bob to complete a semicircular trajectory from here to here, that point. The ratio of the kinetic, okay, wait, semicircular trajectory in the vertical plane with the string becoming slack only on reaching the topmost point. Maybe that means tension is becoming zero. Obtain an expression for I. They're asking what is this V naught value and the speeds at point B and C and ratios of kinetic energies of point B and point C. And what is the nature of trajectory of the bob after it reaches the point C. Let's see. There are two external forces on the bob, that is gravity and tension in the string. Two external forces, that is the gravity and the tension. The latter, that is tension, does no work since the displacement of the bob is always normal to the string. The potential energy of the bob is thus associated with the gravitational force only. The total mechanical energy E of the system is conserved. We take potential energy of the system to be zero at the lowest point A. Thus at A, E, which is equals to, we consider, since we only need to know change in potential energy, one of the point we can consider as zero. That is one of the merits in taking change in potential energy instead of actual potential energy itself. E, which is equals to half mv square, since potential energy is zero at the lowest point. According to Newton's second law, the tension is a type of force. Newton's second law, Ta minus mg, which is equals to mv naught square by L. that is tension at the initial point. Okay, this is due to Newton's second law. They somehow derived this, where Ta is the tension in the string A at a highest point C. Okay, wait, tension of Ta is tension at at point A. Then at the highest point of C, the string slackens, meaning the tension in the string becomes zero. Thus, at C, where E, which is equals to half mv square, there is also potential energy. Mg, which is equals to mvc square by L. Vc is the speed at C from equations 5.13 and 5.14. Energy, which is equals to 5 by 2 mgl from these equations. Equating this to energy at A, 5 by 2 mgl is equals to m by 2 v naught square. V naught, we will get it as v naught root of 5 gl. From this equation here, it is clear from equation 5.14, this one, that Vc, which is equals to root of gl, at B, the energy, which is equals to sum of kinetic energy plus mgl, equating this to the energy at A and employing the result 1, namely v naught square is equals to 5 gl, we will get the energy at B, which is equals to 5 by 2 mgl, and Vb, which is equals to root of 3 gl. By dividing them, we will get it to be 3 by 1. At point C, the string becomes slack and the velocity of the bob is horizontal to the left. If the connection of the string is cut at this instant, the bob will execute a projectile motion with horizontal projection akin to a rock kicked horizontally from the edge of a cliff. Otherwise, the bob will continue on its circular path and complete the revolution. Okay, let's see that again. The first thing we need to know, at the initial position at point A, that is here, at this point, there are two forces acting, that is the tension as well as the gravitational force. Those are the two forces acting. At point C, the tension will become zero because, as they say, the string slackens. Because of that, there is no tension, meaning that if we cut the string at that point, if there was a cliff, if there was a rock on a cliff like this and you just kicked it like this, the stone will follow a path like this, a trajectory, like the trajectory is a projectile motion, projectile motion or something like that. And similarly here, if we cut the string here, then the path will be something like this. That is the trajectory. Now let's go back to the sum problem here. And there are two external forces acting on this bob, gravity and tension force T in the string. The latter does no work, meaning tension does no work, because the angle between displacement or velocity and the direction of force is 90 degrees, so the tension does no work. The total mechanical energy E of the system is conserved. we take the potential energy of the system to be 0 at the lowest point. They're saying that we will take a potential energy of the system to be 0 at the lowest point. With the radius of the circle, they take it as L. They take it as L, and energy at point A, which is equals to half mv naught square, and okay, this is basically centrifugal force formula, not centripetal force formula, mv naught square by r, mv square by r, centripetal force formula. Why this? This was there in the laws of motion chapter, where we saw why an object undergoes circular motion. An object undergoes circular motion because there is a force acting towards the center. The center force is mv square by r. Mv square by r, since the radius is L here, they took it as L. And this centripetal force, which is equal to the force exerted by the motion, something like that. Mv naught square by L, which is equals to tension minus mg. Okay, tension is the force acting upward. If we take a free body diagram of this one, a bob, this is tension A at point A, mg down, and the total net force acting is upward. Actually it's not upward, the net force will become 0 because it's not moving downward or upward. But since the net outward force, which is equals to this much, that is Ta minus mg, that is the force, and this is equal to the centripetal force. So where Ta is the tension in the string A at the highest point C, the string slackens. At C there is no tension force, and the only force acting is mg downwards. At C the tension becomes 0, and energy, which is equals to half mv square plus, assuming this is exactly placed at the ground, the distance here is from the ground, so we take it as 2 mgl. It's basically mgh, but since diameter of the vertical circle here is 2l, we take it as mg into 2l, that is 2 mgl, that is a potential energy. And kinetic energy, if we take, it is half mc square, where here, since there is only one force acting, the mg, which is equal to the centripetal force. Here, as I said before, one more time, the particle is moving in circular motion because there is a force acting on it towards the center. It may be string force at one instant, it may be tension force at another instant, it may be gravitational force at one more instant, it may be any other kind of force. In this case, we can see that clearly. In this case, the centripetal force, which is tension force, or the subtraction of tension minus mg, that is a force that is acting towards the center. It is acting upward or something like that. In this case, there is no tension force. That does not mean the centripetal force is gone. It means mg, which is acting as a centripetal force. Mg, which is acting as a centripetal force. That is why mg, which is equals to, at this point, mg, which is equals to vc square by L. Here it is v naught, that is the initial velocity based on Newton's second law, where vc is the speed at point C from equations 1.5.13. That is the potential energy plus kinetic energy, and this equation here we get that E, which is equals to 5 by 2 mgl. How we get that is because we substitute the value of v here, like in this equation it's there, right? It is the centripetal force, cancel here, so we get vc whole square is equals to g times L, and in this case where v square, if we substitute, we will get E, which is equals to half mgl plus 2 mgl. This we will get it as 2.5 mgl or 5 by 2 mgl. This 5 by 2 mgl, which is equals to m by 2 v naught square. How we can say this value, which is equals to this initial value, how we say that is because conservation of the mechanical energy, the total mechanical energy of the system is conserved. So we say that this energy is equals to m by 2 v naught square. Then we will get v naught is equals to root of 5 gl. It is clear, like in case of yes, this only I did this one. From this equation we know that vc value we get as root of gl, or vc square is equal to gl. That is what I wrote here. And energy, which is equals to at b, point B, energy which is equals to potential energy as well as kinetic energy. The potential energy here, in case we only take L here, we'll only take L here because there is only this much distance here. In this case at point C there was this much height, but in this case there is only this much height from ground, so it is L. And we'll get as mgl, energy, total energy, and half same as how we equated the energy of the at point C to the total energy of the system. We found out at point A, we equate the energy at point A to the total energy at point B. We will get that when we substitute value of VB, velocity at B, which if we do cancel m and m, here we got total energy is this much, and mg, which is equals to centripetal force. But here in this case, energy, the total energy of the particle or the bob, which is equals to half mv d square plus mgl. Okay, they are saying that from first equation, that is this one here, which is E naught, this value we will get it as value of V naught, we will get it as V naught square, we will get it as 5GL. This equation where 5 by 2 mgl is equals to m by 2 V naught square. This is the total energy of the system, and we will get V naught as equal to root of 5GL. Okay. How we got this value is because we got this from the C point where the mg is acting as a centripetal force, mv square c mc square by L. From there we'll get Vc value, and this value is substitute here, we'll get total energy of the system, which is equal to 5 by 2 mgl. And from this we will get V naught value to be root of 5gl when we compare total energy of the system at the initial point. And total energy at particle B, yes, anyways, E, which is equals to half mvb square plus mgl, and this is the total energy of the system. We already got the total energy of the system as 5 by 2 mgl. They complicated it by again writing as 1 by 2 mv naught square, instead of writing the value which we already found out, that is 5 by 2 mgl. That is what they wrote here, half mvb square plus mgl, which is equals to 5 by 2 mgl. From this, if we take the value of vb square, we will get vb which is equals to vb square, which is equals to 3gl, and vb which is equals to root of 3gl, where g is the acceleration due to gravity, L is the radius of the vertical motion or something. And a ratio of kinetic energies, initial kinetic energy half mvb square, we know vb which is root 3 of gl, mvc which we know it is root 5 of gl, no, vc which is root of gl, so I'll get it as 3 by 1. And the last question, that is the trajectory of the bob after, if we cut the string at point C, the trajectory will be, as we are kicking a stone from a cliff, it will follow a projectile motion. I'll read it again just in case. At point C, the string becomes slack and the velocity of the bob is horizontal and to the left. If the connecting string is cut at this instant, the bob will execute a projectile motion with horizontal projection akin to a rock kicked horizontally from the edge of a cliff. Otherwise, the bob will continue on its circular path and complete the revolution. Now that is the topic. Now there seems to be a more of the chapter left. I'll be continuing after a break of 10 minutes. Okay, then it was a break larger than expected. Let's continue. A potential energy of a spring. The spring force is an example of a variable force which is conservative. They're saying that spring force, it is a variable force and it is an example of a conservative force. Figure 5.7 shows a block attached to a spring and resting on a smooth horizontal surface. 5.7, that is this diagram here, this is a smooth surface, frictionless surface. It is attached like this. It is resting there. The other end of the spring is attached to a rigid wall. One end of the spring is attached to the block and the other end is attached to a rigid wall, meaning it is fixed. The spring is light and may be treated as massless. It is a massless spring, an ideal spring. In an ideal spring, in an ideal spring, the spring the spring force Fs is proportional to x, where x is the displacement of the block from the equilibrium position. The displacement could either be positive, that is towards the spring, or away from the spring. Or either negative. This force law for spring is called as Hooke's law and is mathematically stated as Fs, which is equals to minus k of x. Okay. F of s, the force due to a spring, which is equals to constant k times x, where x is displacement, where k is called the spring constant. Its unit is Newton per meter. The spring is said to be stiff, very strong if k is large, and soft, easy spring like pen springs if k is small. Suppose that we pull the black block outwards as in figure 5.7b. We are pulling the spring outward, the block is pulling outward, the displacement is x in this direction. In this case, the force is in this direction. If the extension is xm, the work done by the spring force is equals to minus k of x dx, and when we integrate k of k will come out, it's a constant. Integration from 0 to xm, where x, when we differentiate x with respect to dx, we will get the answer to be is equals to x square by 2. That is why we got the force, which is minus x square by 2. This expression may also be obtained by considering the area of the triangle as in figure 5.7. Note that the work done by external pulling force is positive since it overcomes the spring force. Okay, this is a figure shown here. The plot of Fs versus x, the area of shaded triangle, represents the work done by spring force. Due to opposing signs of Fs and x, the work done is negative. This is the force here. The force is acting like this. The force is negative, work done by the spring, and the extension is this much. Since the area is here, the work done will be negative. By considering the area of this triangle here. The same is true when the spring is compressed with a displacement xc, where xc which is smaller than 0, the spring force does work Ws, which is equals to K minus Kx c square by 2, same, while the external force F does plus Kx c square by 2 if the block is moved from an initial position xi to final position fx. The work done by the spring force Ws, which is equals to minus Kx square by F, K square Kx F square by 2. Thus, the work done by the spring force depends only on the endpoint, specifically where the block is pulled from x initial and allowed to return to x final. Here, why we got kx in final minus kx initial minus kx final, and why in the before force we did not get the minus final or something like that, is because in this case we consider one point to be 0. We took integration limits as 0 to x of m, but in this second case we took from x initial to x final. Here as well we can take from x initial to x final, so we will get the force. So the work done by spring, which is equal to 0. The work done by spring in a cyclic process is 0. Like when you when you first stretch a string and leave it back, then the work done by that spring is 0 because there is no displacement. We have explicitly demonstrated that the spring force is position dependent only at first stated by Hooke, that is f of s, which is equals to minus kx, does work which only depends on the initial and final positions. Example figure 5.17. Thus, the spring force is a conservative force. The force of the spring depends only on the initial and final points. That is the reason why the total work done, like when you leave in a cyclic way, when you stretch a string and leave it back, the work done is 0. The work done on the spring is 0. There is no displacement there, or by the spring is 0. Now the diagrams, other diagrams as well. This here it is stretched, here it is compressed. The spring force Fs is 0 when the displacement x from equilibrium position is 0. For stretched spring, x is greater than 0 and Fs is lesser than 0. For compressed spring, x is greater than 0 and Fs is greater than 0. X is smaller than 0 and Fs is greater than 0. And we define the potential energy of the spring to be 0 when the block we define the potential energy V of x of the spring to be 0 when block and spring system is in the equilibrium position. When it is neither stretched nor compressed, both the spring and the block, that is the spring system, are in equilibrium position. For an extension or compression x, the above analysis suggests that V of x, which is equals to kx square by 2. You may easily verify that minus dv by dx, which is equals to minus kx. The spring force, if the block of mass m in figure 5.7 is extended to xm and released from rest, then its total mechanical energy at any arbitrary point x, where x lies between minus of xm and plus of xm, will be given by half kxm square, which is equals to half kx2 square plus half mv square. Okay, they're saying that the mechanical energy at any arbitrary point, like any point that lies between minus xm and plus xm, will be given by the energy, which is equals to half of kx square plus half of mv square, where we have invoked the conservation of mechanical energy. This suggests that the speed and kinetic energy will be maximum at the equilibrium position x equals 0, where Vm is the maximum speed, or Vm, which is equals to root of k by m xm. Note that k by m has a dimensions of time power minus 2, and our equation is dimensionally correct. The kinetic energy gets converted to potential energy, and vice versa. However, the total mechanical energy remains constant. This is the case like in the ball case or before case, but just in a different scenario. There is a spring here depicted in figure 5.8. This is the parabolic plot of potential energy V and kinetic energy K of block attached to a spring obeying Hooke's law. The two plots are complementary, one decreasing as the other increases. The total mechanical energy, E, which is equals to K plus V, remains constant. If we see here, from minus xm, where at this point the potential energy, yes, this is the blue color one, is the kinetic energy graph, where at near zero it is maximum, and at completely stretched positions it is minimum. This is the black one, is the potential energy graph plot, where at this position it is maximum at minus xm, it is maximum at compressed state, and as it goes to the equilibrium position it goes to zero, and this is converted into kinetic energy completely, and they get interchanged like this, get transformed as one increases the other decreases. To simulate car accidents, auto manufacturers studied the collisions of moving cars with mounted springs of different spring constants. Consider a typical simulation with a car of mass 1000 kg moving with a speed 18 km per hour on a smooth road and colliding with a horizontally mounted spring of spring constant 5.25 into 10 power 3 Newton per meter. What is the maximum compression of the spring? Okay, there is like car manufacturers or auto manufacturers, same thing, automobile manufacturers. These people, they study, they simulate car accidents to study the different cars mounted with different springs constants. Like consider like if there is a kind of simulation going on like that. One kind of simulation is a car with 1000 kg mass. The mass of the car is 1000 kg and it is moving with a speed of 18 km per hour, that is 5 meter per second, on a smooth road, frictionless road, It is colliding with a horizontal mounted spring or spring constant 5.25 into 10 power 3 Newton per meter. They gave K value, they gave mass, they gave speed. Then what is the maximum expression of compression of the spring? At maximum compression by the kinetic energy of the car is converted entirely into the potential energy of the spring. The kinetic energy of the moving car, which is equals to half mv square. We know the kinetic energy, we will get it as every value we have. You will get it as 1.25 into 10 power 4 joule. 10 power 4 joule or 12,500 joules, where we have considered 18 km per hour as 5 meter per second. It is useful to remember that 36 km per hour is 10 meter per second. At a maximum compression xm, the potential energy V of the spring is equal to the kinetic energy K of the moving car from the principle of conservation of mechanical energy. V which is equals to half kx square by m, and V they gave K value. We know kinetic energy as well. Spring constant we know. Now substituting that, we will obtain that half kx m square, which is equals to 1.25 into 10 power 4 joule. Substituting in this equation potential energy, the energy which is equals to, we will get it as 2 meter. Since we know K value which is equals to 10 power 3, 1.25 into 10, 12.5, 12.5 by 2, 24, 24 by 5.25, we will get it as 2 meter. We note that we have idealized the situation. The spring is considered to be massless. The surface has been considered to possess a negligible friction, that is a frictionless. We conclude this section by making a few remarks on conservative forces. Remarks about conservation forces. Information on time is absent from above discussions. In the example considered above, we can calculate the compression but not the time over which the compression occurs. A solution of Newton's second law for the system is required for temporal information. Okay, they're saying that we know that when the cars collide, there will be a compression of the spring, but we don't know like how much time the compression of the spring will take place. We do not know that. We need to use the Newton's second law to find at how much time it will take for the spring to be compressed. Not all forces are conservative. Friction, for example, is a non-conservative force. The principle of conservation of energy will have to be modified in this case. This is illustrated in example for 5.9. Okay. Friction is a non-conservative force. The principle of conservation of energy should be modified when there is a friction in that case. The zero of the potential energy is arbitrary. It is set according to convenience. For the spring force we took V of x equals 0 at x equals 0, that is unstretched string has 0 potential energy. For the constant gravitational force mg, we took V equals 0 on the Earth's surface. In the later chapter we shall see that for the force to the universal law of gravitation, the 0 is the best defined at an infinite distance from the gravitational source. However, once the 0 of the potential energy is fixed in a given discussion, must be consistently adhere to throughout the discussion. You cannot change horses in midstream. Okay, what they're saying is potential energy, we set 0 in here, like we set 0, so we should keep it as 0. Like we are only considering change in potential energy. So initial potential energy at Earth's surface we consider at 0. At equilibrium position of spring we consider it as 0. And we will later see that was a mistake. Like in case of gravitation chapter, we will see that if two masses are separated by infinite distance, the potential difference between them is zero. But it is easier in our normal cases to set the initial potential as zero in these kind of cases to find the potential difference. It is much more convenient to take it as zero. That is why we take it as zero. But after taking it as zero throughout the whole problem, we should keep it as zero. We should not change the value that they have described, saying that you cannot change horses in midstream. Anyways, now consider example 5.8, taking the coefficient of friction mu to be 0.5 calculate the maximum compression of the spring. Same example, same problem, but if there is a friction that is 0.5, coefficient of friction, there is frictional force. In presence of friction, both the spring force and the frictional force act so to oppose the compression of the spring as shown in figure 5.9. We invoke the work energy theorem rather than the conservation of mechanical energy. The change in kinetic energy, this is the car, it is going with like this way with 5 meter per second square. The force is acting on the car, changing kinetic energy, which is equals to 0 minus half mv square. Final kinetic energy, since the car will stop, will be 0. Initial is minus half mv square. The work done by the next net force, which is equals to minus half kx square m minus mu m gxm. Okay. A change in kinetic energy, which is equals to work done. The same work done in case of the work done on the car due to the spring and frictional force, that is due to spring also we can take that, we took it as half kxm square, that is the spring force, work done by spring, and mu mgx, this is the frictional force, mu times n for this car is mg, and not sure why we took xm here. Okay, we took xm because this is force and times distance, which is work done. Force times distance is work done. This much is force, this much is distance. Force times distance, totally work done. This is also work done. This is the spring work done. Both, if we add, both are negative values. So when we add them, we will get work done. Equating this, these are both work done. Both should be equal. So you should get half mv square, which is equals to half kx square. We just cancel the minus. Half mv square, which is equals to half kxm square plus mu mgxm square. Now we know like all the values, I believe, like we know mass of the car, which is 1000 kg, velocity is 5 meter per second. K value we know, it was given, it was some 5.25 or something. Mu value they gave it as 0.5, mass which is 1000, gravitation which is 10 we can take. What we need to find is xm value, mu mg, which is equal to 0.5 into 10 power 3 into 10, which is equals to 5 into 10 power 3 Newton. After rearranging the above equation, we will get the unknown value, that's xm. We will get xm, which is equals to whatever this equation is, where we take the positive square root since xm is positive. Putting in numerical values, all the values we know, we will get xm, which is equals to 1.35 meter. Before we got it as 2 meter without friction, but now with the friction we get it as 1.35, which is as expected, less than the result. For example 5.28, that is 2 meters, it is less than 2 meters, that is 1.35. If two forces on if the two forces on the body consists of a conservative force Fv and non-conservative force FNC, the conservation of the mechanical energy formula will have to be modified by the work energy theorem, that is by this one, by total energy, total change in energy, which is equals to the total force, the net force acting times distance, where E is the total mechanical energy over the path assumes the form E final minus E initial is equals to the work done by the total forces, that is conservative as well as the non-conservative, where W and C is the total work done by the non-conservative force over the path. Note that unlike the conservation force, W and C depends on the particular path I to F. Unlike conservative forces, non-conservative forces like friction depend on the path followed. They do not. They depend on the path followed. There are, I believe, 1, 2, 3, 4 more pages left. So I'll try to complete it today itself. Now, power. Often it is interesting to know not only the work done on an object but also the rate at which the work is done. We say a person is physically fit if he not only climbs 4 floors of a building but climbs them fast. Power is defined as the time, rate at which work is done or energy is transferred. Okay, what is power is? Like in a general sense, power is like we say a human or a person is powerful when he climbs the, like an example, let's say instead of rock climbing, let's take climbing the floors of a climbing stairs or something like that. If two persons A and B, A person climbs 4 floors of stairs in 1 minute, whereas the other person climbs in 5 minutes. When comparing A and B, we can say A is more powerful because it takes less time. So, in physical sense or in physics, power is defined as the rate at which work is done or energy is transferred. The rate at which energy is transferred, dissipated, consumed, that is in electricity, but power is defined as the rate at which work is done. The rate at which work is done is called as power. The average power of a force is defined as the ratio of work W to the total time T taken. P, which is equals to P average, which is equals to work done by time. The instantaneous power is defined as the limiting value of the average power as time intervals approach 0, delta W by delta T, limit delta T reaches 0. And that can be written as P, which is equals to dW by dt, small work and small time interval. The work dW done by friction F for displacement dr is dW. F dot dr, the instantaneous power, can also be expressed as F dot dr by dt or F dot v. Okay, we can the work done by a force F for a displacement dr. If there is a force F for some displacement dr, it will do some work F dot dr. The instantaneous power, which is dW by dt, we can also write as F dot dr by dt. Dr by dt is position vector by time. So the dx by dt or dr by dt we can write as velocity, where v is the instantaneous velocity when there is a force of F. Power, like work and energy, is a scalar. Its dimensions are ml square t power minus 3. In the SI unit, it is called as a watt. The watt is equivalent to 1 joule per second. The unit of power is named after James Watt, one of the innovators of steam engine in the 18th century. There is another unit of power, namely horsepower, HP, 1 HP, which is equals to 746 watt. This unit is still used to describe the output of automobiles, bikes, etc., cars, etc. We encounter the unit watt when we buy electrical goods such as bulbs, heaters, and refrigerators. A 100-watt bulb, which is on for 10 hours, uses 1 kilowatt hour of energy. 100 watt times 10 hours, which is 1000 watt hour, so 1 kilowatt hour. Which 1 kilowatt hour, which is 1 unit, which is 1 kilowatt, which is equals to 10 power 3, and 1 hour is 3600 seconds, so 3.6 into 10 power 6 joule. Our electricity bills carry the energy consumption in units of kWh. Note that kilowatt hour is a unit of energy and not of power. Kilowatt hour is a unit of energy and not power. An elevator can carry a maximum load of 1800 kg. Elevator plus passengers is moving with a speed of 2 meters per second. The frictional force opposing the motion is 4000 Newton. Determine the minimum power delivered by the motor to the elevator in watts as well as in horsepower. Okay, the frictional force is acting downwards. If the elevator takes people up, it's moving up with a constant speed of 2 meters per second. It's moving up. The weight of the elevator, people plus elevator, is 1800 kg. So the force acting downwards is the frictional force, and the weight, that is basically the gravitational force. The total force, which is mg plus m friction, which is 1800 into gravitational acceleration due to gravity, that is 10, you will get as 22,000 Newton or 22 kilonewton. The motor must supply enough power to balance the force. Hence, P, which is equals to force into velocity. We know that velocity is 2 meters per second. Power, which is equals to force, that is 22,000 into 2, that is 44,000 watt, that is same as 59 HP. So we can say that if there is a consumption 44,000 watt, very large. Now let's go to the next topic, that is collisions. Collisions in physics, we study motion change in position. At the same time, we try to discover physical quantities which do not change in a physical process. Okay, the laws of momentum and energy conservation are typical examples. In this section, we shall apply these laws to commonly encountered phenomena. What they are saying is, like in physics, we study motion, that is change in position. We study the change in position, that is called motion, and at the same time, we try to discover physical quantities which do not change in a physical process. Laws of momentum, that is change in momentum, and energy conservation. Energy, momentum is also conserved, energy is also conserved. They are changing, but they will be remain constant. They will not change in a physical process. In this section, we shall apply this laws of energy and momentum conservation in normal daily phenomena, that is Collisions. Several games such as billiards, marbles, or carom involve collisions. We shall study a collision of two masses in an idealized form. Consider two masses m1 and m2. The particle m1 is moving with a speed vi, no, vi1, the subscript I implying initial. We can consider m2 to be at rest. No loss of generality is involved in making such a selection. In this situation, the mass m1 collides with stationary mass m2, and this is depicted in figure 5.10. Okay, one mass is moving, another mass is at rest. The mass first one is moving with a velocity of v initial 1, and it will collide with the second mass that is at rest. In this situation, mass mass m1 collides with stationary m2, and this is depicted in figure 5.10, collision of mass m1 with a stationary m2, where we can say mass m1 will go in this direction with theta 1 angle, that is, and with another velocity of v1f, here v1 final, and this one with theta 2 with v2f. The masses m1 and m2 fly off in different directions. We shall see that there are relationships which connect the masses, the velocities, and the angles. Now let's cover the subtopic in the last topic: elastic and inelastic collisions. In all collisions, the total linear momentum is conserved. The initial momentum of the system is equal to the final momentum of the system. One can argue that this as follows: when two objects collide, the mutual impulsive forces acting over the collision time delta t causes a change in their respective momenta. The impulse acting on them will cause a change in their momenta, where F12 is the force exerted on the first particle by a second particle, F21 is likewise the force exerted on the second particle by the first particle. And now from Newton's third law, we know that forces are equal. The forces due to one object on other object is equal to the force on other object due to the same object. That is, but different in direction. This implies that delta P1, change in momentum of 1, like the first object plus the change in momentum of the second object, should be equal to 0. The above collision is true even though the forces vary in complex fashion during the collision time delta t. So the third law is true at every instant. The total impulse on the first object is equal and opposite to that on the second. On the other hand, the total kinetic energy of the system is not necessarily conserved. The impact and deformation during collision may generate heat and sound. Part of the initial kinetic energy is transformed into other forms of energy. A useful, like when we see collisions, there are large amount of heats generated or sounds generated. This will dissipate the energy. A useful way, or deformations, like when two cars collide, the car will get deformed very much. This happens to reduce the energy. The energy is reduced very much. To visualize the deformation during collision is in terms of compressed spring. If the spring connecting the two masses regains the original shape without loss in energy, then the initial kinetic energy is equal to the final kinetic energy, but the kinetic energy during the collision time t, delta t, is not constant. In case of a spring, if we see, once we compress a spring, it will get released to its, like when we release it again, it will come back to its original position. So kinetic energy is conserved. But that's not the case like In reality situation, that is not possible for collisions. Such a collision is called as an elastic collision. That is when it is like a spring. On the other hand, the deformation may not be relieved if what if the spring was malfunctional or something like that, and after compression it did not come out completely, or it did not get restored to equilibrium position at all, then that's not an elastic collision or anything like that. Like in real life situations, this deformation may not be relieved and the two bodies could move together after collisions. A collisions in which two particles move together after the collision is called a completely inelastic collision. The intermediate case, where the deformation is partly relieved and some of the initial kinetic energy is lost, is more common and is appropriately called an inelastic collision. Okay, what they are saying here is elastic collision is basically a spring. Another way, for another hand, like deformation may not be relieved and the two bodies could move together after the collision. The two bodies attaining same velocity and moving together. A collision where the two particles move together is called a completely inelastic collision. When there is a completely inelastic collision, the two bodies are attached, like become attached to each other. They do not get attached to each other. They move together. The intermediate case, where the deformation is partly relieved and some of the initial kinetic energy is lost, more common and is appropriately called like that is a completely inelastic collision. That is not mostly seen in real life situations. A real life situation is inelastic collision, not completely inelastic collision. In the inelastic collision case, incomplete inelastic collision, where after collision some of the initial kinetic energy is lost. That's pretty much all. Collisions in one dimension. Collisions in one dimension consider a first a completely inelastic collision in one dimension. Then in figure 5.10, they give the figure. Yes, this one. Figure 5.10. Theta 1 is equals to theta 2, which is equals to 0. Okay. M1 V1F, which is equals to M1 plus V2 V final, momentum conservation. Vf, which is equals to M1 by M1 plus M2 VLI or V1I. We are finding final velocity based on momentum conservation. The loss in kinetic energy in collision, delta K, which is this much, half M1 V1 square minus half M1 plus M2 V square F final velocity, the total mass. Where if this kinetic energy loss is 0, it is an elastic collision, where we can write this as, we can just substitute it and write it as minus half M1 square by M1 plus M2 from this equation, where we got V final, which is equals to M1 by M1 plus M2 times VLI. I mean V initial first one. And taking half m1 v1 initial whole square, we will get 1 minus m1 by m1 plus m2. This we write it as m1 m2 by m1 plus m2, which is positive quantity as expected. Consider next an elastic collision using the above nomenclature with theta 1 is equals to theta 2 is equals to 0. The momentum and the kinetic energy of conservation of equations are m1 initial, which is equals to m1 v1 final plus m2 v2 final. Complete conservation, momentum conservation. We'll get this, and now we are squaring the velocities. From equations 5.23 and 5.24, it follows that m1 v1i times v2 minus v1i, which is equals to m1 v1f. Okay, these are kinetic energy equations for a elastic collision. They just cancel 2 here, as 2 is common, they just cancelled it off. And from these equations they derived any velocity value, I believe. Let's see more. v2f after doing some substitutions, we will get that the final velocity of the second particle, which we will get as the sum of the initial and final velocity of the first particle. Substituting this equation in 5.23, this equation, we will get that v1f, that is equals to m1 minus m2 by m1 plus m2 times v initial of the first particle, and v2f, the second particle, we will get it as 2m1 v1i by m1 plus m2. Thus the unknowns v1f and v2f are obtained in terms of knowns m1, m2 and v1f, I mean v1i. Okay, they are finding, we do not know these second particles final or the initial particles final. We only know that the second particle was at rest initially. What we do not know are the final of the initial particle and final velocity of the second particle. In this equation, if we see, we cannot find the value of, we can actually find value of V1F, like 1F. Further simplification, M1 got cancelled. Fine, I'll see this later again. Special cases of our analysis, if the two masses are equal and V1F is equal to 0, V2F is equal to V1 initial, the first mass comes to rest and pushes off the second mass with its initial speed on collision. If one mass dominates, example M2 is very large, the first case both masses are equal, then first mass comes to rest and pushes off the second mass with its initial speed of collision. That is in case of the perfectly elastic collision. In the second case, if like one mass is completely like very heavy, the heavier mass is undisturbed while the lighter mass reverses its velocity, like just when hitting a wall or something like that. When you hit the wall, the ball will come back, the wall will not move. Now let's see an example here. Slowing down of neutrons. In a nuclear reactor, a neutron of high speed, typically 10 power 7 meter per second, must be slowed to 10 power 3 meter per second so that it can have high probability of interacting with isotope uranium and causing it to fission. Show that a neutron can lose most of its kinetic energy in elastic collision with a light nuclei like deuterium or carbon, which has a mass of only few times the neutron mass. The material making up the light nuclei, usually heavy water, D2 or graphite, is called a moderator. Okay, this is about nuclear fission, where when neutrons collide with like uranium material, the uranium will get fission, meaning the uranium will fission to form two different smaller elements. This will release large amount of energy. And for higher chances of the neutron to cause the fission, the neutron speed should be around 10 power 3 meter per second, not 10 power 7 meter per second. To reduce the speed from 10 power 7 meter per second to 10 power 3 meter per second, the nuclear reactors use a kind of moderators which reduce the speed, and these are generally made of heavy water or graphite. The initial kinetic energy of neutron, half m1v1f square, while its final kinetic energy, from equation 2.5.26, we will get final kinetic energy as this one. The fractional kinetic energy lost is F1 K1F by K1F K1I, that is this much, while the fractional kinetic energy gained by the moderating nuclei is K2F by KH, or no, not KH, K1I. It is F2, which is equals to 1 minus F1 elastic collision, which will get us 4m1 m2 by m1 plus m2 whole square. One can also verify this result by substituting from equation 5.27. For deuterium, mass is 2m, and we obtain F1, which is equals to 1 by 9, while F2, which is equals to 8 by 9. Almost 90% of the neutron's energy is transferred to deuterium. For carbon, F1, which is equals to 91.6%, and F2, 28.4%. In practice, however, this number is smaller since head-on collisions are rare. This is the only case where there is a head-on collision, but in the reality case, there are not much head-on collisions. If there is initial velocities and final velocities of both the bodies along the same straight line, that is called one-dimensional collision or head-on collision. In the case of small spherical bodies, this is possible. The direction of travel of body 1 passes through the center of body 2, which is at rest. In general, the collisions is two-dimensional, where the initial velocities and the final velocities lie in a plane, means in xy axis or something like that. Collisions in two dimensions. Figure 5.10 also depicts the collision of a moving mass m1 with stationary mass m2. Linear momentum is conserved in such a collision. Since momentum is a vector, this implies three equations for three directions x, y, and z. Consider the plane determined by the final velocity direction of an m1, m2. Choose it to be xy plane. The conservation of the z component of linear momentum implies that the entire collision is in the xy plane. The x and y components are m1 v1 cos theta plus m2 v2 cos theta 2 is equals to m1 m1 v1 final sin theta 1 minus m2 v2 final sin theta 2. One knows m1 m2 v1 f. In most situations, there are thus four unknowns v1 v2 theta 1 and theta 2 and only two equations. If theta 1 is equal to theta 2, we regain equation 5.23 for one-dimensional collision. If further collision is elastic, we will get kinetic energy is equal. Kinetic energy is conserved. We obtain an addition equation that still leaves us one equation short. At least one of the four unknowns, say theta 1, must be made known for the problem to be solvable. For example, theta 1 can be determined by a moving detector in an angular fashion from x to y axis. Given m1 m2 vh theta 1, we can determine u1f v2f theta 2 from equations 5.28 and 5.30. Now let's see the question here. Consider the collision depicted in figure 5.10 to be between two billiard balls with equal masses m1 and m1 equals m2. The first ball is called the cue, while the second ball is called the target. The billiard ball wants to sink the target ball in a corner pocket, which is at an angle theta 2, which is 37 degrees. Assume the collision is elastic and the friction and rotational motion are not important. Obtain theta 1. At what angle we should strike so that the ball will go to the pocket. Basically, making use of these equations here, we will get that these equations, and since the collision is elastic, m1 equals m2, it follows conservation of kinetic energy, that is this one. Comparing equations 5.31 and 5.32, we get cos theta 1 plus 37 degrees is equal to 0, meaning theta 1 plus 37 degrees equals 90 degrees, thus theta 1, which is equals to 53 degrees. This proves the following result: when two equal masses undergo a glancing elastic collision with one of them at rest, after the collision, they will move at right angles to each other. The matter simplifies greatly if we consider spherical masses with smooth surfaces and assume that collision takes place only when the bodies touch each other. This is what happens in the game of marbles, carom, and billiards. In our everyday world, collisions takes place only when two bodies touch each other. But consider a comet coming from far distances to the sun, or alpha particle coming towards a nucleus and going in some direction. Here we have to deal with forces involving action at a distance. Such an event is called as scattering. The velocities and directions in which the two particles go away depend on their initial velocities as well as these type of interactions between them, their masses, shapes, size, and charges as well. Summary: The work energy theorem states that the changes in the kinetic energy of a body is the work done by the net force of the body. The force is conservative if one, work done by it on the body is path independent, depends only on the endpoints, that is, x initial and x final, or two, the work done by the force is zero for an arbitrary closed path taken by the object such that it returns to its initial position, that is a cyclic path. For a conservative force in one dimension, we may define a potential energy function v of x such that f of x, which is equals to minus dv of x by dx. V initial minus V final, which is equals to integration of f of x dx from initial point to final point. The principle of conservation of mechanical energy states that the total mechanical energy of a body remains constant if the only forces that act on the body are conservative. The gravitational potential energy of a particle of mass m at a height x about the Earth's surface is V of x, which is equals to mgx. The variation of g with height is ignored. The elastic potential energy of a spring of a force constant k and extension x is V of x, which is equals to half kx square. The scalar dot product of two vectors a and b is written as a dot b and is a scalar quantity given by a dot b, which is equals to ab cos theta. The theta is the angle between a and b. It can be positive, negative, or zero depending upon the value of theta. The scalar product of two vectors can be interpreted as the first product of magnitude of one vector and component of the other vector on the first vector or unit vectors. Scalar product obey the commutative and the distributive laws. These are the symbols. Work W, dimensions same as energy. Work is equal to scalar product of force into displacement. Kinetic energy half mv square, joule is the unit, k is the symbol. Potential energy V of x. Formula, mechanical energy each is equals to sum of kinetic energy plus potential energy, spring constant mt power minus 2. Potential energy which is equals to potential energy of spring, which is equals to half kx square, and power which is equals to f dot v, scalar product of f dot v. Points to ponder. The phrase calculate the work done is incomplete. We should refer or imply clearly by constant to the work done by a specific force or a group of forces on a given body for a certain displacement. Okay. Okay. The second point, which is work done, is a scalar quantity. It can be positive or negative, unlike mass and kinetic energy, which are positive scalar quantities. The work done by friction or viscous force on a moving body is negative. For two bodies, the sum of mutual forces exerted between them is zero from Newton's third law. Okay, but the sum of the work done by the two forces need not to be always cancel out. However, it may sometimes be true. The work done by a force can be calculated sometimes even if the exact nature of the force is not known. This is clear from example 5.2 where W theorem is used in such a situation. The W theorem, that is work energy theorem, is not independent of Newton's third law, I mean second law. The W theorem may be viewed as a scalar form of the second law. The principle of conservation of mechanical energy may be used as a consequence of the W theorem for conservative forces. The W theorem holds in all inertial frames. It can also be extended to non-inertial frames provided we include the pseudo forces in the calculation of the net force acting on the body under consideration. Basically, this holds true for all initial frames. It can also extend it to non-initial frames, inertial frames, provided we include pseudo forces in calculation of the inertia. Is basically the tendency of the body to not change its position. If in case of non-inertial frame where there exists no inertia, we can include false force as it's not actually a force but inertia. To change this inertia, where instead of representing it as inertia, we're saying it as a pseudo force. When we include pseudo force, it will still remain correct only. The final answer: the potential energy of a body subjected to a conservative force is always undetermined upon a constant. For example, the point where the potential energy is zero is a matter of choice. Yes, we discussed about this. For the gravitational potential energy MGH, the zero of potential energy is chosen to be ground. For spring potential energy kx square by 2, the zero of potential energy is the equilibrium position of the oscillating mass. Every force encountered in mechanics does not have an associated potential energy. For example, work done by friction over a closed path is not zero and no potential energy can be associated with friction. There is no potential energy that is associated with friction. Like not every force has an associated potential energy, a statement. And like example, friction stores no potential energy. During a collision, the total linear momentum is conserved at each instant of the collision. B, the kinetic energy conservation, even if the collision is elastic, applies after the collision is over, does not hold at every instant of the collision. Okay, basically this is also a statement. During a collision, that is the total linear momentum is conserved. Like any instant if we take the total linear momentum, we can say it is conserved. But that does not apply for the kinetic energy. Even if the collision of the total kinetic energy may not be conserved in case of inelastic collisions, it is conserved in case of elastic collisions. But even in elastic collisions, at every instant of time if we take, it is not conserved at every instant of time. In fact, the two colliding bodies are deformed, maybe momentarily at rest with respect to each other. Because there is deformation, it is not completely conserved. Now with that, I have completed work, energy and power. Work, energy and power. First revision via NCERT has been completed. Okay, then I will be ending the stream. Good night.